Hi and welcome to John's Maths Book. In this video, we'll be exploring another key concept in mathematics. If you find this tutorial helpful, then please show your support by subscribing, liking, and leaving a comment. Your positive engagement helps me create more content and allows me to bring you more valuable maths lessons. Without further ado, let's go over to the whiteboard. In this exercise, we're going to find the area between a parabola and a horizontal line. While I appreciate that there are a number of ways of achieving this, I'll be using polar coordinates and double integrals. I'll demonstrate how to formulate the double integrals, and if you stick around until the end of the video, which I hope you will, I'll show you how to evaluate the double integrals. Suppose then we have a parabola with equation y equals x squared and horizontal line with equation y equals 1. When the line intersects with the parabola, a region is created between the two shown here in blue. We are tasked with finding the area of this region. The first step in finding the area is to convert the equation of the parabola and the horizontal line from Cartesian coordinates to polar coordinates. To do this, we'll substitute r cos theta for x and r sin theta for y. Beginning with the parabola, in Cartesian coordinates, we have equation y is equal to x squared. Making the substitution for y and x, we have r sin theta is equal to r squared cos squared theta. And dividing both sides of the equation by r and then cos squared theta gives r equals sin theta divided by cos squared theta. And for the horizontal line in Cartesian coordinates, we have y equals 1. Substituting for y gives r sin theta is equal to 1. And therefore r is equal to 1 divided by sin theta. Now that we've made the conversion from Cartesian to polar coordinates, let's look at the behaviour of the radial distance r as we use it to compute the region shown in blue. As r rotates in a counterclockwise direction from theta equals 0 to theta equals pi, theta being the angle r makes with the x-axis, the radial distance from the origin is determined by the parabola. When the parabola intersects with the horizontal line for the first time, the radial distance from the origin is then determined by the horizontal line until it once again intersects with the parabola for the second time. After the second intersection between the parabola and the horizontal line, the parabola once again determines the radial distance from the origin until the area is complete at theta equals pi. To find the angles at which the horizontal line intersects with the parabola, we can equate the polar equations. Our polar equations are r equals sin theta divided by cos squared theta and r equals 1 divided by sin theta. And equating these gives sin theta divided by cos squared theta is equal to 1 divided by sin theta. And multiplying both sides of the equation by sin theta gives sin squared theta divided by cos squared theta is equal to 1. And using the trig identity where sin theta divided by cos theta is equal to tan theta, we have tan squared theta is equal to 1. And taking the square root of both sides of this equation, we have tan theta is equal to plus or minus 1. So when tan theta is equal to 1, theta is equal to pi by 4, and this is where the horizontal line intersects with the parabola for the first time. And when tan theta is equal to minus 1, theta is equal to 3 pi by 4, and this is where the horizontal line intersects with the parabola for the second time. We're now in a position to start defining the limits of integration as r rotates about theta, and these will be the outer integrals. The area of our region can be defined as the double integral over the region R, where we sum infinitesimally small pieces of area shown as dA. In this case, the region, as we saw, was split into 3 sectors. The first extended from theta equals 0 to theta equals pi by 4, and these become the limits of integration of the first outer integral. The second sector extended between where the parabola intersected with the horizontal line for the first and the second time. So in this case, from theta equals pi by 4 radians to theta equals 3 pi by 4 radians. And these become the limits of integration of the second outer integral. The third sector extended from where the parabola and the horizontal line intersected for the second time, so where theta is equal to 3 pi by 4 radians, to where the area is complete, so at theta equals pi radians. These become the limits of integration of the third outer integral. Now let's look at what happens when we sum infinitesimally small pieces of area along the radial distance or in the r direction. This will help us define the inner integrals. When we integrate or sum in the r direction, this will represent the inner of the three integrals. This diagram represents a sector of the region, capital R. The angle it makes is infinitesimally small and is denoted by d theta. Within the sector, we have infinitesimally small pieces of area denoted by dA. The size of each area is the length multiplied by the width. So in this case, dr is the length and r d theta the width. And so dA is equal to r dr d theta. To find the total area of the sector, we integrate or sum in the r direction. When we sum or integrate along the radial distance r, in this case we begin at the origin and travel along the parabola until it intersects with the horizontal line. So we begin at r equals 0 and end at r equals sine theta divided by cos squared theta. We then sum along the radial distance beginning at the origin and travel along the horizontal line until it intersects with the parabola for the second time. So we begin again at r equals 0 and end at r equals 1 divided by sine theta. Finally, we sum along the radial distance beginning at the origin and travel along the parabola until the area is complete. So we begin at the origin, so where r is equal to 0, and end where r is equal to sine theta divided by cos squared theta. Now we can add the limit of integration when we integrate or sum along the radial distance r for each of our three inner integrals. We saw that in the first, the lower limit was at r equals 0, and our upper limit was at r equals sine theta divided by cos squared theta. In the second, we saw that the lower limit was at r equals 0, and the upper limit was at r equals 1 divided by sine theta. And in the third, we saw that the lower limit was at r equals 0, and the upper limit was at r equals sine theta divided by cos squared theta. And in each case, we're summing infinitesimally small pieces of area, dA, which translates to r dr d theta. We can now start to evaluate the inner integrals. The first of these is the integral from r equals 0 to r equals sine theta divided by cos squared theta, r dr. Using the power rule, the antiderivative of this is r squared divided by 2. And plugging in the limits of integration, we have sine squared theta divided by 2 cos to the power of 4 theta minus 0. And this equals sine squared theta divided by 2 cos to the power of 4 theta. For the second of the inner integrals, we have the integral from r equals 0 to r equals 1 divided by sine theta, r dr. The antiderivative of this is r squared divided by 2. And if we plug in the limits of integration, we have 1 divided by 2 sine squared theta minus 0, which equals 1 divided by 2 sine squared theta. And for the third of the inner integrals, we need to integrate between r equals 0 and r equals sine theta divided by cos squared theta, r dr. The antiderivative of this is r squared divided by 2, and plugging in the limits of integration, we have sine squared theta divided by 2 cos to the power of 4 theta minus 0, and this equals sine squared theta divided by 2 cos to the power of 4 theta. That completes the evaluation of all the inner integrals. Now we can begin work on the outer integrals. So the first of these is the integral from theta equals 0 to theta equals pi by 4. And we're integrating sine squared theta divided by 2 cos to the power of 4 theta d theta. The antiderivative of this is tan cubed theta divided by 6, and plugging in the limits of integration, we have 1/6 minus 0, which equals 1/6. And for the second of the outer integrals, we want to integrate from theta equals pi by 4 radians to theta equals 3 pi by 4 radians, 1 divided by 2 sine squared theta d theta. The antiderivative of this is minus 1 divided by 2 tan theta. If you'd like more details on how to integrate 1 divided by sine squared theta, then please see this video. If we now plug in the limits of integration, we have minus into the bracket of minus a half, and this evaluates to 1. And for the last of the outer integrals, we want to integrate from theta equals 3 pi by 4 radians to theta equals pi radians, sine squared theta divided by 2 cos to the power of 4 theta d theta. The antiderivative of this is tan cubed theta divided by 6, and plugging in the limits of integration we have 0 minus 1/6, and this equals 1/6. So we've now completed the integration process of all 3 double integrals, and we have a result for each of these. Summing the values of 1/6 plus 1 plus 1/6 will give us the result for the area of the blue shaded region. And so summing these values gives us a value of 4/3 for the total area.